Howdy, AP PreCal. It is Miss Kosh. This is the third way that I have taught semi-log plots in the 3 years that this course has existed. So each year I'm kind of refining how I want to do this, and we'll see how this goes today. To begin with, I start introducing the idea here by, I've got this table of data, and you might notice that it's exponential. And then I plotted it, but I intentionally went out to some big numbers. So notice I get up to almost 100,000. So what I needed to do when I graphed it is I needed to scale out to a really large value to get this last point on the graph. Well, that means that you can't really see what's happening in some of these earlier points. They almost just all look like they're on the x-axis. They're not, but because of the scale of the graph, you can't really see what's happening. So then I switched it in Desmos. I had the same exact points, and I put it into what we call, this graph is called a semi-log plot. And so I kept it so that the x-axis, the x values still are linear, but then I scaled the y values to be logarithmic. Okay, and so you'll notice here we have this is 10 to the 0 power, this is 10 to the first power, this is 10 to the second power, the third power, the fourth power, the fifth power, the sixth power. And that enables us to get all of our data represented in a way that where we can see it. We can see what's happening, and it turns the exponential data into something that looks, it's still the same data, but it turns it into something that looks linear. Okay, so here's how we plot on a semi-log plot, excuse me. We have the point 0, 200 would be right here. And so here's the point A. You'll notice I started at 100, and each of these lines goes up by 100 until it gets to 1,000. And these are logarithmically scaled, so they don't have the same, the distance between the lines is not consistent, okay? So our output values have a constant proportional change, but not a constant rate of change. Okay, so the next one, 25. So here would be 10, and so here's 20, here's 30. And so 25 would be halfway between 20 and 30, and that's the point B. 7 means we're going to go 2. This is 1, 2, and so forth. Hang on. So 1, 2, 3, 4, 5, 6, 7. Oh, 6, 7. Oh, sorry. And there's C. Okay, let's see, the one 3.2, 80, that's not 80, that's 800. 3.2 would be somewhere about here. 800 is going to be just a little bit shy of, so this is 1,000, this is 900, so here is 800. So it would be something about here. Let's see how well I did. Was that point D? Yeah, that looks like it's about 3.2. Okay, and then I have a 4.6, 1.5. Well, this is 1, and this is 2. So 4.6, 1.5 would be right about here, and here's point E. Okie dokie. The next one, I have sketched a graph of f of x when they give you this information. Well, so let's start setting this up. If I have log base 5 of f of 3, that's going to be equal to 0. And so this tells us f of 3 will be equal to 5 to the 0 power, which is 1. And then I have log base 5 of f of 4 is equal to 1, which gives us that f of 4 is equal to 5 to the first power is just 5. The next one, maybe you've recognized the pattern. If you haven't, here we're going to do one more. This becomes f of 5 equals 5 squared, which is 25. And so then the last one, f of 6 would be equal to 125 because that's 5 cubed. And so roughly, I didn't do this 1, 2, 3, 4, 5, 6. I need to worry about doing this too closely, but I have the point, when I have an input value of 3, I have an output value of 1, somewhere down there. When I have an input value of 4, I have an output value of 5. Input value of 5, I'm going to have an output value of 25, and then this is going to pretend to be 125. It's something like that. Basically, it's exponential. Okay, and then with these, we notice that this one is exponential, and the question is why? And that what we know is the input values have a constant rate of change. So input values have a constant rate of change. In particular, rate of change. In particular, it's equal to 1. Okay, the output values, I'm going to be lazy, I mean efficient. We're going to change a couple words. The output values have a constant okay. That didn't save me too much time. They have a constant proportional change. In particular, their proportional change is 10. We're multiplying by 10 as we go down. The next one, it's going to be logarithmic because we're switching these two. So we selected me. Okay, so what's happening is these would actually change. So the output values, the output values have a constant rate of change of 1, and the input values have a proportional rate of change. Okay, the next one, this one should look pretty similar. It should look like the one we just we did above a second ago. And so we think, oh, look, it looks linear. Everything, we're adding the same amount each time in the input values. We're adding the same amount each time in the output values, but we're really not. So what happens is this becomes exponential, like this example up here. But what we have is the natural log of f of 1 would be equal to 4, which means f of 1 is equal to e to the 4th. And so then I have the natural log of f of 2 is equal, close the door, please. Close the door, please. I'm making a video. Oh, sorry. You're the best. You're trying to be kind and I'm fussing. Thank you. I have nice colleagues. Okay. And this is equal to 8, so that tells me f of 2 is equal to e to the 8th. And so what the next one, f of 3, ends up being e to the 12th. And we struggled with this a little bit in class, but what we're doing is if I take e to the 4th and multiply it by another e to the 4th, I get e to the 8th. If I take e to the 8th and multiply it by another e to the 4th, I get e to the 12th. And so my kids wanted to say, well, e to the 4th squared is equal to e to the 8th, which is true, but that doesn't help us. That's not what we're multiplying by each time. We just so happen to be able to square one and get the next answer, but that was kind of a fluke, so don't use that sort of reasoning. And this last one is linear. The input values have a constant rate of change, and the output values have a constant rate of change. Okay, maybe I could write linear. All right, let's keep going. So now what we are going to do is we're going to look at linear models of a semilog plot. And so I took the same data from before, and this is exactly what we started with, and we're going to find the average rate of change. But I want to do the average rate of change on this particular graph, and so I don't want to use the actual output values. I don't want to use the actual values from the table because then it wouldn't give me something. My rate of change wouldn't be constant. Okay, let me try that again. What we notice is that if we have a line, our rate of change is going to be constant over that whole line. Okay, and so if I come over here and I find that if I try and find the rate of change and I do 45 minus 15 over 2 minus 1, that equals 30. But if I do 135 minus 45 over 3 minus 2, now we're equaling 90, and that's not the same. And so what we have to do is not look at the actual y values, but take the log of those y values. So this first one, we're going to use the coordinates. This would be the 0.1 comma log of 15, and this would be the 0.2 comma log of 45. Okay, so now when I find the average rate of change, I'm going to say my average rate of change is equal to log of 45 minus log of 15 over 2 minus 1. 2 minus 1 is 1, so I don't really need that. But what I do notice is I can take that log, the subtraction of logs can be squished together with a very precise mathematical term using division. And so that becomes log of 45 over 15, and that reduces to log of 3. Okay, the next one at 3 and 4, I would have, so here would be, this would be the 0.3. and this is log of 135, and then the 4 was 4 comma log of, I think this is 405. Let me verify. It is. Okay, and so I have, this becomes log of 405, the average rate of change, minus log of 135, and it's over 1, but I'm just too lazy to write that. 4 minus 3 is 1. So this would equal log of 405 divided by 135, and hopefully you realize that that's log of 3. Okay, the next one, we had 7 was, this would be 5, well, this is 5 comma log of 1, 2, 1, 5, and then this one here was 7 comma log of 10, 9, 35, and so I have log of 10, 9, 37, 5. Did I remember that? Nope. 10, 9, 3, 5. Okay, minus log of 12, 15, all over 7 minus 5 is equal to 2. Okay, and then now I recognize that this would be equal to 1/2 times log of 10, 9, 3, 5 over 12, 1, 5. And maybe you recognize that that's equal to 9. And so this is 1/2 of log of 9, which the 1/2, the reason I wrote it there is because it can become an exponent, and the square root of 9 is equal to log of 3. So all of these have have the same rate of change, because, and if we think about it, our line was linear, they should have a constant rate of change. So now let's look at this next one. We said we know that a line, y equals mx plus b, that m is the slope, or it's the rate of change. Well, our rate of change we just found was log 3. And then our y-intercept, well, we had this point. What was this very first one? This is the point 0, 5, but we don't want to use 0, 5. We need to take the log of that to make things linear. So we're going to have 0 log of 5, so the y-intercept is log of 5. And so this, ladies and gentlemen, is our linear model for that data. Now, it has messed with my head for a while. Okay, hang on. I'm jumping ahead of myself. Let's manipulate that a bit. I can come here and rewrite this as x times log of 3 plus log of 5. And then I can say that this is log of 3 to the x plus log of 5. And then what I can say is this is log of 5 times 3 to the x. I could put it this way, whatever. And now I might notice that that's gonna be the equation of the exponential model. Y equals 5 times 3 to the x. And maybe you noticed that from looking at the data to begin with. Our initial, this was, if we think sequences, like a geometric sequence, g sub 0 is 5, and our common ratio, was 3, which gives us that equation. Isn't that lovely? But it has bothered me that we have we let y equal this and y equal that. And so I went and talked to one of my colleagues, and she was helpful and was like, think of y as just the output value, but they might mean different things. So for example, this a times b to the x would be equal to f of x. And then when you take the log of everything, it's actually equal, the output value is now log of f of x. Okay, and so they're not, these y values don't mean the same thing. Okay, I had a couple multiple choice problems from Mr. Passwater. So on this one, they're saying he's told a joke, and here the things are plotted on the logarithmically scaled graph. And so since it appears linear, we know that it's going to have to be exponential. This is not exponential, and this is not exponential. So then what we did in class today is we said, well, this would be the point 0, 2. And this would be the point 1, 1, 2, 3, 2, 3, 4. I started to do that wrong. And so when I plug in p of 0 right here, would be 2 plus 2 to the 0, which is 2 to the 0 is 1, so this would equal 3, which is not what we want. We wanted to have 2. So let's see this one. P of 0 would be 2 times 2 to the 0 is 1, times 2 is 2, and that's our correct answer. The next one, all that we have to really look at is that it's logarithmically scaled, and we can eliminate 2 of these choices. This one is linearly scaled. Sorry. So we're going up by 0.5, so that's no good. This one is also, this is going up by 50, which is cool, but not a semi-log plot. And then now I'm looking at these two. One of them is going to go up to 1,000. The other one's only going up to 10, but our data goes up to 200. So the correct answer, I had a lot of clutter there. Let me get rid of some of that. The correct answer is D. All right. Like, subscribe, and go practice. Good luck to you.